Fellow mathematicians, lesson 4, class notes, and then I will model some of the homework in a separate video. So today's lesson is about quadratic roots. And this idea of quadratic roots is really a synonym for lots of different things, which is why you're going to see that line, or those three kind of fill in the blanks that are also called. So let's talk about roots, what that means, and then we'll do a little bit of graphing, and then I'll model some of the homework notes. So first of all, if I think about a review and really what we've done thus far, we have done something like this. If I just show you my little sticky note review. Up till now, we have identified a quadratic. A quadratic term is, we have a variable that is to the second power. We have equations that might include that term, whether there are additional terms like our bx term or our c. A quadratic has to have a variable to a second power or degree. Now, the second thing we learned was an actual equation itself in standard form. So we have this as our standard form. If you see this, which you will all throughout your math careers, the ax squared plus bx plus c, oftentimes we want to even get an equation into the standard form because it gives us information about the equation and even what we're modeling in real life. What we can tell from the standard form is we can pretty easily find the vertex. So again, remember the vertex is the turning point of a parabola that, it's going to be something like that, and the vertex will be right here. This is going to be a minimum value because it's on the bottom. We can find the vertex by using this formula, which is the axis of symmetry formula, but really what this is giving us is the x. Like, what is x and where on our coordinate grid will x be? If I get an x by using this formula and just plugging in some of these values, then whatever I get for x, I can plug in to my original equation and then solve for y. Suddenly, if I have an x and I have a y, I put them together, I have a coordinate pair, which is our vertex. From there, once I have a vertex, I could create a table, which we've done the past couple of lessons. I could create a table of values. And then I can go ahead and graph it on the coordinate plane, which is like right here. And I can analyze it. It can give me information, etc. It's enabling me, when I graph it, to find the actual solutions to the quadratic. And we're going to talk about what a solution really means in a minute. The other thing that we've learned about is a different form, and that's called the vertex form. So you're going to see this throughout your career as well. Now, vertex form looks a little bit different, and if you were with me in class, we studied this quite a bit, where we have this x that has been now kind of modified, if you think about it. I'm subtracting, maybe I'm adding, but I have this new value in here, which is h. And that h is an h on purpose because it tells us how horizontally it will move as contextualized by our parent function. And then k, we learned that if we add a k, for example, it's going to move up as relatively speaking compared to the parent function. This determines the vertex, so it can give us the vertex really quickly, like h comma k. And it also can tell us how it's transformed or even changed or even different from our parent, that y equals x squared. Whether it dilates, meaning stretching or compression. Maybe it's reflecting, because I have maybe a negative or positive a. Or maybe I'm translating it, which is a fancy word for sliding it back and forth and up and down. So this vertex form tells us a lot of information about what it actually looks like. Then I can go ahead and graph it using the vertex and doing similar things to what we did with the standard form. Well, today we are going to learn something different. And we're just going to expand on our idea of what does it mean to actually have a solution. So if I look at this word roots, you're going to hear about this a lot. I'm sure you've heard square roots, and we are rooted into the ground. If I think about what that word actually means, I drew a really, really pretty picture of a tree here. that is maybe branching off. Maybe this is my quadratic and I have my roots down here that anchor it, right, into the soil. Sometimes I have lots of roots. If I don't have a root, if it's not anchored into the soil, then my tree probably falls over. So maybe that's a good analogy to think about what a root means as far as quadratic equations are concerned. So quadratic roots, and it is plural, is this. They are the points at which the parabola intersects the x-axis. So, and again, the axis, which is x, is going to be on that horizon. So again, think of a tree that's being rooted into that horizontal plane. And if I have an intersect here, well, hey, that looks like I have two roots. Now, there are other words for this that you are going to hear. The other words you're going to hear for this are, first of all, solutions. Oh, so right there, as soon as it touches the x, that's a solution. Okay. Well, we could also call this the x-intercepts. And hopefully that makes sense because this is where it is rooted in. This is where the solution is rooted into the x-intercept, which is the horizon. We also call these zeros. And you may be thinking, well, what is actually zero? Well, if I look up here, what would be zero? Is it the y or the x or what have you? So keep that in mind when we start diving into this world. So you can have a number of solutions, or there's information that will tell us very quickly if there are solutions and how many there might be. So if I look visually at the types of graphs, quadratics, that I will see, you are going to see things like this. Well, let's do a parabola like this. This is a positive. I'm going to have a positive A because it's pointing up. And check this out. It is rooted in two places. So I have two roots here. I could say I have two solutions here. I could say I have two zeros here, right? What is actually zero here? Is it the value of x or is it actually y? So be thinking about that. Now, if I think about one solution, or what the actual word root means, if I think about one solution, then that means it's got to touch in maybe one particular place. So let's draw something like this. So does this touch the horizon or the x-axis at one particular place? Well, it does, and it's right there. So our parent function, I'll draw another one right here. It looks like this, doesn't it? Well, that has one solution too, or that has one root or one zero, and maybe I'll even do this one because this is our negative parent, right? It's kind of like y equals negative x squared. Yep. So all of these, if they touch at one place, just has one root or one solution. Last but not least, if you think ahead about, well, what do you think makes it a non-solution? Well, when it doesn't do all of this stuff. So draw some examples. What about that? Does that have a solution? Well, I can graph it, but does it have a root? Is it rooted into our x-axis? And the answer is no. How about something like that? No. If it touches the x-axis, even if it's really close, these are all no. They don't have solutions, meaning they don't touch the x-axis. So down here, let's do one together with some examples. So right here it says find the solutions of the following quadratics by graphing. Okay, so here I'm going to go back to that whole idea of finding my x. So don't forget that formula because that will give us our x value. So let's see, my negative b would be negative 4. So again, you can go ahead and list some of your values if it does help, which I think it always does, and then you can plug them in. So x equals Well, negative b is negative 4 over 2 times 1. And negative 4 divided by 2 is negative 2. So x is negative 2. Now I'm going to put my vertex in the middle row. I'm going to add 1 as I go up, subtract 1 as I go down. If I plug negative 2 back in, which I am going to show you in 1, if I plug negative 2 back in here, well, y equals negative 2 squared plus 4 times negative 2 minus 5. Y equals 4 plus negative 8. It's always good to keep your signs and numbers in parentheses. Minus 5. Y equals, well, it seems like I have negative 4 minus 5 is negative 13. And then 4, so I'm going to end up with negative 9. Okay, so after I plugged it in, my y, x is negative 2, and my y is negative 9. So I'm going to go ahead and put those in. I am not going to model every single value on this because you can do it. And remember, once you have one side, you can find the other side. That's what it's going to look like. So our solutions, remember our solutions are where the y is 0. Well, that y is 0 and that y is 0. So if I go back up here to our definition, well, what's at zeros? Well, I'm actually going to write, this is where the y equals 0, just to make sure that is not where like the x's are zeros or anything. So you can use the table to find out where your y's are 0. That's one way to do it. You can go ahead and graph it. So if I do go down to graph it, if my x is, let's see, if I go back 2 and down 9, well, I think this is a 10 grid, so I'm just going to go down 1, and then I start graphing some of these. If I go 0 down, negative 5, 1, 2, yep, and then I'm going to go on this side, because I'm going to have 1, 2, 3, 4, 1, 2, 3, 4, 5. I'm going to have something like this, right? And I could graph every single piece out, but where they should meet, so our roots, where they should meet is at the following places. So I should meet at 1, right here, and then I should meet at negative 5. 1, 2, 3, 4, I was close, right here. So that is my solution, where my roots end up on my x. How we write this is like this. X equals, so I'm going to make a set. So this bracket actually gives us information that what we're looking for is a set. Now this is not a coordinate because it's not in parentheses. This is a set. That means that my x is negative 5 and 1. These are my two x's, my x-intercepts, where they meet the x-axis. And this is where my y's are 0. These are the solutions. I'm just going to do that one. If I go to the next page, though, there's another little tip I would like to teach you, and it has a fancy term, and it's called the discriminant. The discriminant is a very fancy term, and if I think about discriminant, I think about something that's kind of different. And maybe the discriminant will give me vital information. I feel like it should be a movie. Here's another tip, though. The discriminant is used to determine the number of solutions. So if I have a question on the SAT, for example, it just says how many solutions are in this quadratic equation? How many solutions are there? Are there any? This is a quick way to do that. And I got there are many different formulas and standard forms, but this is something that you are going to see a lot in a term. So the discriminant is this. So this is based on our standard form. So all I'm really doing is I'm realizing that this is a formula. That if I plug in some of those values from a standard form quadratic equation, I can quickly tell if there are no solutions, one solution, or two solutions. So it's a quick fix. If so D over here stands for the discriminant, otherwise known as D, right? Because that's another variable. We like variables in algebra. If D is greater than 1, so if I plug in my values from my standard form and I suddenly work it out and I get that it's greater than 1, then that means that there are multiple solutions, which makes sense. But there are two solutions, but just think greater than 0, two solutions. If this equals 0, then that just means there's one solution, which when you are solving any equation, if you get to 0, that typically means that, oh yeah, that equals that, so that's one solution. If you get this value and it's less than 0, then that means there aren't any solutions. Doesn't mean game over, but it just means it's not crossing the x-axis. There's no intercept there. That's when you may have that weird thing that's way up here. It's like hanging on for dear life in the second quadrant without any anchor to it. So example, so I'll do maybe 1 or 2 and then I'll call it, but I'm going to go ahead and plug in. So remember this formula, and down here I'm going to remind you that it is really good practice to identify your B's, your A's, your C's. I'm going to need them all this time. So your B is 5. Your A, actually I would do it in that order, A, B, C. Forgive me, I didn't. Your A though is 1 and your C is 4 in this particular example. And now we're just going to plug them in to this formula. So I should have 5 squared minus 4. And now in parentheses, I'm going to put those two values for A and for C. So A is 1 and C is 4. And now we keep going. So 5 squared is 25. Negative 4 times 4 is negative 16 times 1. So I get 25 minus 16. And the difference between the two is 9. Now let's think to ourselves. So D is 9, right? So D equals 9. Well, remember, if there is one solution or one answer that is over 0, that means there are two solutions, right? So I got one answer. That means I have two solutions. Let's do one more. So here I have, I'm going to do it in order this time. A is 1, B is negative 3, and C is 10. And I'm going to plug it in. So I should have negative 3 squared, and it's good, again, to put it in parentheses, especially when you have negative signs, minus 4, and I'm going to multiply 1 times the C value, which is 10. Negative 3 squared is 9. Add all this together, is negative 40, and I end up with negative 31. So D is negative 31. Well, that's less than 0. That's pretty small. So that means there are no solutions. So to recap what we just did, and then that's the homework. Okay, so recap what we just did. The discriminant, you can use this formula simply to determine the nature of the solutions. If there are 2, 1, or 0, it's not a big solution. It's part of a greater solution that we're going to learn about later called the quadratic equation that we're going to learn about later. Good luck, but you can follow along when I do the homework if you wish.